true projects. In this video, we are going to explain about the project that is WSA YOLO, Weak Supervised and Adaptive Object Detection in the Low Light Environment for YOLO V7. Before getting into the execution, first let us understand what is the project about. Now think about object detection like a person trying to find an object in a room. So during the day or in a good lightning, it is pretty easy for both the humans and also machines to spot the things. But if the light goes out, or the room gets foggy, things get harder to see. Similarly, object detection models like YOLO, they work well when there is enough light. But when the light conditions change, like in the low light or foggy environments, they start to struggle. This happens because the models are mostly trained on the normal lightning conditions, that is normal images. When the lights, when the light drops, the objects in the image they lose contrast, and there is more noise in the images, which makes the models tough to figure out what is the object in the image. And we do have some methods to sort this issue, that are histogram equalization, filtering, and improving brightness methods. But there are flaws too. So when we try to fix this issue by using basic image techniques like adjusting brightness or contrast, but these methods only go so far. They help to make the image clear, but they don't really help the model to understand important parts of the image, like where the object begins or ends. So deep learning helps here because it is smarter and it can recognize patterns, but it comes with its own challenges. For example, it needs lot of data to train, lot of images that are already labeled with what the objects are, which is time consuming and requires powerful computers. Even then, the model can still miss important details in the low light images because it doesn't fully see all the features that would make the detection easier. So this issue is the traditional methods don't fully adapt to the needs of object detection, and even with the advanced deep learning models, the low light images still hide information that makes detection harder. So imagine you're trying to use an object detection in real time, say for a drone flying around or autonomous car driving in the night. If the lighting is bad, like it is foggy or it is nighttime, the system could easily miss the things like pedestrian or an obstacle in the road, because the current models just aren't built to handle those tricky conditions. So this brings us a couple of problems. First, many current systems are slow or they can't keep up in real time. They might struggle when constantly changing environments, like car driving through different lighting conditions or drone flying over various terrains. So these systems also tend to bulky and not very scalable, meaning they can't easily adapt or expand to handle larger or more complex environments. What we really need is the systems that are not only accurate but lightweight and efficient too. They need to work well even when the lightning is bad, so they can be trusted in real life situations like drone inspections, autonomous vehicles, or remote sensing tasks. Without solving these challenges, we can't really rely on these models in dynamic, unpredictable environments. So this is why improving the adaptability and performance of object detection in low light or complex conditions is so important. It is about making these systems more reliable and practical for everyday use. So to overcome with all these issues, this project proposes WSA YOLO V7. It proposes YOLO V7. It is designed to handle those tough low light conditions more effectively. And what it does is it uses a pretty smart method, that is weak supervision. It uses weak supervision that doesn't rely on as much label data, which makes it more adaptable. And it also uses something called adaptive enhancement techniques. Basically, it tries to adjust the image to make the important details stand out even in the poor lighting. To do this, it separates the image into two parts, that is reflectance and illumination maps. So reflectance is which how the light interacts with the object, and illumination, which is the overall lighting of the scene. By separating these components, the algorithm can enhance each part more effectively, improving the final image for detection. And the WSA YOLO model has some really clever components that make it work well in the low light situations. First, it introduces something called adaptive residual feature block, that is ARFB. So think it like a tool that allows the model to compare and find relationship between images taken in low light and those in the normal light. This helps the system recognize patterns even when the light is poor, and it makes the whole process more efficient. Next, the parameter prediction block has been taken, which boosts the model's ability to reuse its features, making the process, that is whole process, faster and more efficient. This means the model doesn't need to relearn everything from scratch each time, saving resources and improving the performance. And then adaptive adjustment block. So this is combined with a consistency loss function. So this adaptive adjustment block is combined with the consistency loss function. So this part does some important fine tuning. It helps brighten up the image, reduce noise like the grainy look you get in the dark photos, and make sure that important details of the image are preserved so the object can still be detected clearly. Finally, the model uses YOLO. So finally, the model uses YOLO framework, which is great for classifying objects and makes predictions even in tough conditions. And to measure how well it performs, the model is evaluated using metrics called mean average precision, and recall. This gives us a clear idea of how accurately the model is detecting objects and whether it is doing so in reliable way or not. And to further improve the performance of this project, we are incorporating multiple models of, multiple versions of the YOLO, that are YOLO V5S6, YOLO V5X6, and YOLO V8, YOLO V9, which is an advanced version. These versions are used to dive deeper into the performance of object detection in low light conditions. The goal is to see how these newer models stack up in terms of accuracy and efficiency, especially in challenging environments where visibility is limited. So these are used to increase the accuracy purpose. And furthermore, to develop the front end of the project, we have used Flash framework. This interface allows users to interact easily with the system and test its capabilities. With secure authentication, users can log in, perform evaluations, and get hands-on experience with how well the system works in different scenarios. This provides a more practical and accessible way for users to test out the system, making it easier to understand and its performance and potential. So this is the extension part. Moving on to the implementation. To implement this project, we have followed set of steps mentioned in the flow of work. So first what we have done is we have imported the required packages for image processing, model training, and front-end development. Then comes the exploring the dataset part where we load the dataset, that is we load the images into the system for processing, and we visualize those images to get an understanding of the data. Then comes image processing, where we convert the images into a format suitable for the YOLO model using a blob object that represents the image as multi-dimensional matrix. Then comes defining the class. So this assigns classes or categories to the objects that model should detect, that is cars, pedestrians, etc. Then comes declaring the bounding box. Here we define the coordinates for bounding boxes that will be used to label the detected objects in the image. And then we convert array to NumPy array. So here we convert the image data into a NumPy array, which is a standard format for handling image data in deep learning. Then we load pre-trained model. So here we load pre-trained YOLO model and read its architecture. Then we identify and extract the output layer from the network that will produce the final detection results. Then comes image processing part. So here we combine the images with their corresponding annotation files, which contain the information about objects in the images, that is their class and the bounding box coordinates. Then we convert image which is in the BGR format to RGB format. So BGR color format is used by OpenCV to RGB format, that is standard for deep learning models. Here, then we create mask. So we create a mask that highlights the region of the image where the object is located. Then we resize the image to fit the input size required by the model. Then we do basic data augmentation where we apply random transformations like flipping or shifting to increase the diversity of the training data. Then comes rotating the image. So we apply random transformations to simulate different object orientations. Coming to transforming the image, we apply other transformations such as scaling or cropping to improve the robustness of the model. Then comes installing the packages required. So here we install any additional libraries and tools that are needed for training and deploying the model, such as TensorFlow, Keras, or PyTorch. Then comes processing the data based on YOLO families. So we format the data according to YOLO specific requirements for input and output, ensuring the compatibility with the model. Then comes building the model. So here we define and build the YOLO based object detection model. This step involves setting up the architecture of the model and configuring the YOLO model for training purpose. Then comes training the model. So here we train the model using prepared data set, adjust the weights and parameters to minimize the loss function and improve the detection accuracy. And the best YOLO version will be saved for the future use in the detection. So we will be saving the best performing YOLO model for future detection tasks. And coming to the part of front end. So We have developed front-end using Flash framework, which provides user-friendly interface for interacting with the model, and we set up registration and login functionality with the SQLite database for user authentication and management. And users, they will be able to upload images in the front end for detection purpose that will be pre-processed at the back end. It will be fed to the trained model. Finally, trained model will be detecting the objects and that will be displayed to the front end of the application. So this is how we have implemented the project. Now coming on to the algorithms used. So these are the algorithms used in this project to detect the objects. That is SSD, faster, RCNN, YOLOV3, YOLOV5, YOLOV7, and the proposed model YOLOV7 WSA. And these are the extension models, that is YOLOV5S6, YOLOV5X6, YOLOV8, and YOLOV9. And to implement this project, we need basic requirements, which are hardware and software. So coming to hardware, we need operating system of Windows, processor of i5 and above, RAM of 8 GB and above, and hard disk of 25 GB and above. And coming to software, we need application of Anaconda, primary language of Python, front-end framework of Flask, back-end framework of Jupyter Notebook, database SQLite 3, and front-end technologies are HTML, CSS, JavaScript, and Bootstrap 4. So this is the overview of the project. Now let's execute. To execute, we are supposed to open the code folder that contains source code files. So let's open the code folder of the project. So these are the source code files in the code folder of the project. Let us understand each of them. How will they be used in this project? So in the sample folder, we have the test cases that we will be using in the front end. So these are the images that we will be using in the front end for detecting the objects. Let's get back. And here in the static folder, we have files related to CSS, JavaScript, and Bootstrap files, which are important for the visual appeal. And here in the templates folder, we have HTML templates that are used in this project. For example, index.html, about.html, etc. And that will be rendered in this project. Then here in this YOLO V5 folder, we have the data set that is used in this project. So let's open this YOLO V8 folder. That is, sorry, YOLO V5 folder. So here the data is in two subfolders. One is train and the other one is validation. So let us open the train folder. So here we have two more subfolders. One is images and the other one is labels. Let us open the image folder. Here, these are the images which are used to train the YOLO V5 model. So these are the low lightning images that are used to train the YOLO V5 model to detect the objects. Let's get back. So that objects we will be detecting, locations we will be having in this label files that we call as annotations. So here in this label folder, we have the files containing annotations or labels for objects in the corresponding images. So here each label file, it corresponds to an image file in the image folder. For example, this first label file, it contains the objects, I mean object annotations of first image. So this object's annotations we will be having in the first annotation file. Similarly, for the second image, we will be having in the second annotation file. Accordingly, for all the images which are in this train folder, that are 731 images, we have 731 annotation files. So these label files, they follow the YOLO format. So let's open a file for sample. So here each line specifies a detected object. So as there are 4 lines here 4 objects are detected in the image. So here each line is followed by object class index and its bounding box coordinates, which are normalized to image dimensions. So this is the object class index and these are the bounding box coordinates. So this is the x limit, y limit, width, and the height. So this is one type of object where class 2 refers to one type of object and class 5 refers to another type of object. Similarly, we will be having in all other annotation files. I mean label files. Let's get back. So images which are in the train folder are used to train the models and images which are in the validation folder are used to evaluate the trained model. Let's get back. And the same images we do have in YOLO V7, YOLO V8 and YOLO V9, but they are annotated differently because each YOLO version requires its own specific type of image annotation for training and testing the models effectively. Having separate data set, I mean having separate folders helps keeping the data set organized, ensuring that each YOLO version receives the correct annotations it needs to function properly. So this is about the data set and here we have app.py file. So this .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in HTML templates. And these three are the model files in which we have algorithm information that is stored in the that is stored in these files, and they will be loaded into the project code during runtime of the application. And this is the notebook file, which is a Jupyter notebook file which contain a combination of code, graphs, and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for the data science. And this is the signup.db file. This file is a database file which is used to store the user information. So this is about the code folder. Now let us execute. So copy the path of the code folder from the address bar of the file explorer. I'm copying it. Now open Anaconda prompt. So give the command cd. I mean, here Anaconda prompt is open. Now give the command cd, give the space, paste the copied path. Now click on enter. Here you can observe that current directory is changed to the code folder's path. Now we are supposed to compile app.py file. So give the command python space app.py and now click on enter. This command will execute Python script and perform a runtime check for any syntax errors or logical issues. And after running the app.py file, Flask framework will host the application locally at the default address, which is the local host and the port unless configured differently. So just wait for a while. File is being compiled. So here at this default address, the application has been generated, hosted. So this is the local host and this is the port. So now copy this Flask framework's generated link. So copy this link generated by Flask framework and now paste it in any web browser. I prefer Google Chrome, so I'll paste it in that. Paste the link here, click on enter. And this is the web page of the project, which is displayed in the browser. This is developed using Flask framework. Now we need to get registered first. So click on register and enter all the registration details if you are registering newly. I have already registered, so I'll directly sign in. Click on sign in. Give your username and the password. Click on login. We have logged in successfully and we are redirected to detection page of the project. So here you can see a choose file button, right? We need to click on that for uploading the images. So click on choose file. So these are the images. Now we will be uploading them for the detection of objects in the images. So let's upload the first image. Click on open. Here it has been loaded. Now click on upload. So what happens now is the image will be pre-processed at the backend. It will be fed it to the train model and then train model will be detecting the objects in the image. So just wait for a while. File is being pre-processed at the backend. So here we got the detection. So here we can observe that there are three detections. One bicycle has been detected. So here you can observe that image is in low light condition, right? It's in a dark room where a bicycle is detected and two other objects are detected. Bicycle is detected in white color bounding box and the other objects are detected in pink color with the 0.98 probability score. Probability score is nothing but it is the confidence level that how accurate the detection is. So now let's get back. Let's upload some more. So now let's upload this image. Click on open and now upload it. So here we got the detection. You can observe that four cars have been detected and three bicycles are detected. Multiple persons are detected. You can observe, right? Cars are detected in green color bounding box, bicycle in white color, person in the red color. You can observe, right? Here are the persons. So it is detecting in red color bounding box. Let us upload some more. So now let's upload this image. So here you can observe, right, images in very dark condition, very low light condition. So here there are multiple bicycles. So here it is detecting multiple bicycles and drawing a bounding box around the bicycle. Let's get back and upload some more. Click on choose file. So now let us upload this image where it is very dark. Click on upload. So here you can observe that multiple people are detected and bicycles are detected. You can observe, right? So here persons are detected and also bicycles are detected. You can observe lightly that here persons are present. And also they are riding the bicycles. Let's get back. Now let's upload some more. So now let's upload this image. Click on open and now upload it. So here we got the detection. You can observe, right, a person sitting here. So it is detected in red color bounding box and bicycle is detected. Here is a bicycle. So it is detected in red color bounding box. Let's upload some more. Click on choose file. So, so now let's upload this image. So here there are multiple boats. So that is why it is detecting boards and drawing a blue color bounding box. You can observe, right? Let's upload some more. Click on choose file. So now let's upload this image. Click on open and now upload it. So here you can observe, right? Other vehicles are detected. So that is why it is drawing a pink color bounding box around it. Let's upload some more. So now let's upload this image. Click on open and now upload it. So here bicycle is detected. Here there are multiple bicycles. So that is why it is detecting bicycle around it. So let's upload some more. So now let's upload this one. Click on open and now upload it. So here you can observe bottle is being detected. You can observe, right? A blue color bounding box is drawn around the bottle. Click on choose file. Let's upload from the down. So now let's upload this image. Now click on upload and detect. So here we got the detection. You can observe, right? A person is detected and a bottle is detected and here computers are detected as other objects. You can observe, right? So this is how you need to execute the project. Now let's check with the graphs. Click on graph. So here the first graph which we have is the precision score confidence curve graph. And this is the recall confidence curve graph. This is the FN score confidence curve graph. And this is the confusion matrix. And here we have precision score comparison graph. Here on x-axis we have precision score and on y-axis we have all the algorithms that are trained. So here is the graph and this is the recall score comparison graph. This is the mean average precision comparison graph. So mean average precision and recall are the evaluation metrics used to evaluate this project. So now click on logout. In this way, by giving the images of low light conditions to this application, it will accurately detect what is the object in that image and give you the detection, that is bounding boxes. That is what is that object. So this is all about the project.
Thank you for watching video. For more projects please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.